Hello, this is Earl Nestor T. Velasquez of B12, and today I'm going to discuss about frequency division multiplexing, its concepts, its FDM system, its FDM hierarchy, and its application. Let us start. Multiplexing is a way of sending multiple signals or streams of information over a communications link at the same time in the form of a single complex signal. The higher the data rate, the more cost-effective the trans facility is. In this case, the possibility of sending a number of signals is more. The signals are combined into one and are sent over a link which has a greater bandwidth of media than the communicating nodes. As you can see from the image below, the receiver recovers the separate signals. This process is called demultiplexing or demuxing. In analog radio transmission, signals are commonly multiplexed using frequency division multiplexing or FDM. A number of signals are transmitted at the same time or simultaneously on the same medium, and each source transfers its signal in the allotted frequency range. There is a suitable frequency gap between the two adjacent signals to avoid overlapping. Each signal is modulated to a different carrier frequency. Since the signals are transmitted in allotted time, so this decreases the probability of collision. The frequency spectrum is divided into several logic channels, in which every user feels that they possess a particular bandwidth. In this, the useful bandwidth of medium should exceed required bandwidth of channels. The carrier frequencies are separated so signals do not overlap. Therefore, to avoid interference between two successive channels, guard bands are used. An example is FM radio and CATV. Channels are allocated even if there are no data. Let us continue with how frequency division multiplexing works. The transmission channel bandwidth is divided into a number of frequency slots. As you can see from the image, these are divided into 6 channels: Channel 1, Channel 2, Channel 3, Channel 4, Channel 5, and Channel 6. It is renamed from F1 to F6. Each of slots can accommodate the signal of an individual connection. The multiplexer assigns a frequency slot to each connection and uses modulation to place the signal of the connection in the appropriate slot. Each individual signals occupy W hertz. As you can see from the diagram below, ABC is from 0 W hertz. Moving on, the operation of frequency division multiplexing is based on sharing the available bandwidth of a common communication channel among the signals to be transmitted. This leads us to the FDM systems. The first in the FDM system is the FDM transmitter. The block diagram of the FDM transmitter is seen below. It goes from the first modulate to the multiplexer and to the second modulate. Each signal that needs to be sent over a communication channel undergoes modulation with various carrier frequency. As shown clearly in the diagram below, signal 1 goes to the carrier FC1, signal 2 goes to the carrier FC2, signal 3 goes to the carrier FC3, and signal N, which N signifies the number of signal that goes through, goes to the carrier FCN. There are different kinds of modulation, such as amplitude modulation, pulse modulation, and frequency modulation. As the name suggests, the modulation done in this diagram is frequency modulation by the FDM transmitter. These modulated signals are then added up using a linear adder or a mixer. The linear mixer is different from the normal mixers. Here, the sum and the difference of frequency components are not produced, but only the algebraic addition of the modulated outputs will take place. Different signals are thus added together in the time domain, but they have a separate identity in the frequency domain. The composite signal at the output of the mixer is transmitted over the single communication channel, as you can see in the figure. This signal can be used to modulate a radio transmitter if the FDM signal is to be transmitted through air. Moving on to the next part of the FDM systems, we have the FDM receiver. The block diagram of an FDM receiver is shown below. Unlike the first, the FDM receiver process goes from the first demodulate to the demultiplexer to the second demodulate. At the receiving end, the single composite signal is received by the FDM receiver. The receiver then passes the composite signals through various bandpass filters. As you can see, we have BPF1, BPF2, BPF3, and BPFN, which N signifies how many numbers of carrier signals has been transmitted. Each of these bandpass filters has a frequency corresponding to the frequencies of one of the carrier waves. The bandpass filters have an adequate bandwidth to pass all the channel information without any distortion. Each bandpass filter will accept the signal whose frequency matches with the frequency of the carrier signal and rejects all other channels. The signal coming out of a bandpass filter passes through a demodulator. The demodulator does the work of separating the original signal from the carrier signal. The output is then the original signal that has been transmitted. Next, in toll telephone service, voice signals are transmitted over high-capacity channels using FDM. The telephone FDM technique illustrated in this slide is adopted by the American Telephones and Telegraph Company, or AT&T. The American Telephone and Telegraph Company provides the vast majority of long-distance services in North America. AT&T analog carrier system used a hierarchy of FDM schemes. The first higher-level FDM hierarchy is the basic group. It is the first multiplexing step for combining message signals. A basic group consists of 12 voice channels, multiplexed together by stacking them next to each other in the frequency domain. 12 4 kHz voice band channels occupy a combined frequency bandwidth of 48 kHz. It ranges from 60 kHz to 108 kHz. Next, higher-level FDM hierarchy is the supergroup, which is formed by frequency division multiplexing 65 groups containing 60 channels between 312 kHz and 552 kHz. Lastly, is the master group, which is composed of 10 supergroups of combined 2.52 MHz bandwidth between 564 kHz and 308 kHz. For the last part, we will now discuss the applications for FDM. FDM is used for FM and AM radio broadcasting. Each AM and FM radio station uses a different carrier frequency. In AM broadcasting, these frequencies use a special band from 530 to 1700 kHz. All these signals are multiplexed and are transmitted in air. A receiver receives all these signals but tunes only one which is required. Similarly, FM broadcasting uses a bandwidth of 88 to 108 MHz. FDM is also commonly used in television broadcasting or TV networks. It is also found in the first generation cellular telephone. With that said, this is now where we conclude the discussion for frequency division multiplexing. I hope you have learned something from the discussion. Once again, I am Earl Nestor Velasquez of B12. Thank you for listening.